All right, I just want to list everything first. All right, so kinetic energy, it's going to be 22 and a half eV. And I want to know the strength of the magnetic field. That's 4.55 times 10 to the minus 4 Tesla. And figure out the period of this motion. I want to kill myself already. All right. All right, that's it. Did you ever have a test where the professors will give you like 3 problems? The fourth one is the one that you're supposed to come up with on your own and be able to solve it. And then when you start to work on it, only to realize that that's the only one that you're not able to solve. Yeah. So none of you guys went to a real school?
Nope. Going to Wabanza.
Oh, okay. So yeah. So I had a friend who was going to dentistry school, and then they had to take physics evidently, and then he was really struggling with physics. So evidently his professor gave him that option, and then he came up with a problem. He couldn't solve it, so he had to come find me and say, "We can't already solve this." I'm thinking, well, why would you come up with something that you don't know how to solve? So this brings us to this problem right now. All right. So how would you solve a problem like this? All right. The first thing I want to do is just convert this to joules. All right. Yeah. All right. So conversion factor is going to be this. All right, so somebody do the conversion, just give me the number. All right, so here's what we will do. We will do a direct approach. That's what I like to do usually. All right, so what would be the direct approach for a problem like this? I don't know. All right, so figure out the period of this motion. All right, give me some suggestions. Period is the amount of time it takes for it to make a single revolution, right? So the amount of time it takes for it to make a single revolution, that's it. That's your period. All right, so a couple of things to know. It's got a radius. This is going to be a negative charge. And obviously it's going to be moving at a given speed. The only thing I'm interested in is the period. Oh my God, how do you find the period? It's straightforward, guys. Does it have speed? Of course it does. What is speed? I believe the speed is distance over time. That's it. Wait till it's vanished. Okay, cool. So what that means is the speed is going to be the time it takes for it to actually make this circle, right? So here's your C. What is C? Circumference. All right, so how long does it take for it to actually travel that distance? It takes T happens to be the period. So the amount of time it takes for it to actually complete the circuit is what the period is. Got it? That's it. So that's what we will have to do. All right, so it's got speed. It's got speed, my man. All right, so the speed is going to be circumference divided by the time it takes for it to complete, traverse the circumference, which is going to be your T, or the period. Let's make sure that they have the same symbols. And solve for that. And then boom. Life is so easy. All right. That's it. Okay, we're done. So C is going to be 2 pi r. And V. The only thing we have to do now is figure out what V is. V is right here, V is right here. All right, so how do you figure out V? Well, once again, it's always the same trick. Oh my God, it's circular motion. If it's circular motion, can you figure out V? Yeah, it's a piece of cake. So what causes circular motion? The centripetal force does. So question, what is the centripetal force in this case? In this case, the centripetal force is the magnetic force. All right, so it's the magnetic force. All right, so V is what we need to figure out. So how do we do that? All right, so boom, boom, boom. So let's figure that out. So centripetal force is the same as the magnetic force. Centripetal force is going to be mv squared divided by r. The magnetic force in this case is going to be, I'm going to call this q, v, and then we have v. All right, so it's going to be q v v times the sine of the angle between the velocity vector and the magnetic field. All right, in my notations, let me just place the magnetic field going into the page. And identify the force. All right, that's it. So the force is directed towards the center. Okay, so velocity vector is moving in this direction. The magnetic field is going to the page. So what's the angle between them? It's going to be 90 degrees. Sine of 90 degrees is going to be 1. All right, so right, so that term becomes 1. All right, so what is it that we are solving for? We are interested in V. All right, so let's isolate V from M. I got my cancellations, get rid of M, multiply both sides by R, and that's it. All right, so get rid of these two. All right, so what do we have? We will have Q, R, B divided by M. Q, R, B divided by M. Okay, good enough. All right, so what do we do? Substitution. And that's it. So we have 2 pi R divided by this new expression. So you have QRB. All right, so M is the denominator of a denominator, so I'm just going to pull it up. And then once again, oh shit, R does not matter. This is so weird. Evidently, the radius does not matter in terms of the period of this motion. So 2 pi. Let me just get rid of the like terms first. Mass does matter. Charge matters, and that's it. All right, so this is the period of this motion. Evidently, the radius doesn't matter. Wow. Only thing that matters is the strength of the magnetic field. All right, so now that we've done the math, let's do a little bit of thinking regarding this. Guys, the only thing you get to control externally, believe it or not, is the strength of the magnetic field. The stronger the magnetic field is, the smaller the period is, the smaller the duration is, which means that the faster the charge is going to move. And how fast the charge is moving is not dependent on the radius. It's kind of weird. It's not dependent on the radius. All right, so this one and this one is going to take the same time, or will it? What do you think?
Yeah.
All right. I mean, it's on all appearance that the radius doesn't matter, right? And this one, whatever the time it takes for this one is going to take the same time. But that means that the one in the outer region is actually moving faster.
Unless the magnetic field's weaker.
Okay, I'll give you 10 points for that one. Damn, Ian, I'm going to dismiss you from this class. You're becoming too smart for these lectures. You're just making connections way too fast. And obviously you're thinking, wait a minute, is it possible that the magnetic field is getting too weak with respect to that point? We'll find out. It's kind of weird. All right, so this just gives you an idea how to put together these concepts in order to solve these problems. All right, so, how do you find the frequency if that's the case? Frequency is the number of cycles per second, number of periods per second. It's the reciprocal of a period is going to give the frequency. All right, so that's it. Okay, so this is the frequency looks like this. All right, I'm done with that. Kind of lost interest in this problem, so let's move forward. All right, let's focus on this one. This one is kind of neat.
So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. You get an inward force. If I reverse the direction of the current, we expect an outward force. Get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you see. Right-hand rule, simplified.
He's using the same right-hand rule that I showed you guys, all right? You flatten the fingers, but normally, I mean, current is moving this way, the magnetic field is moving this way, and these fingers will point in the direction of the force. Us physicists usually prefer to use that as opposed to using the calc one. All right, so it was a nice little demonstration. All right, so you got the magnetic field coming out of the page. No current, absolutely no current. And then as soon as there's current in the wire, notice that there's going to be a deflection to the right. Reverse the direction, another deflection to the left. It's exactly the same as the right-hand rule number 1 that I gave you guys. All right, so how does that go? What you need to do is imagine that the current is going in this direction, in the upward direction. which means that the charges are flowing in that direction. So thumb points in that direction. And the fingers will be lined up in the direction of the magnetic field. In this case, the magnetic field is coming out of the page towards you guys. And notice that your palm, my palm in this case, is pointing to my left, to your right. You can move your fingers in this direction, and then this is going to give you the direction of the force, for example. It's the same idea. All right, so mathematically, how does this look? Looks kind of neat. All right, so let's go here and go to lecture, chapter number 20, lectures. All right, so you will find the derivations, some of the derivations here. Okay, so this one is its easy derivation, straightforward derivation. So you get the magnetic force acting on a current carrying wire. All right, so the only thing you get to focus on literally is this positive charge. All right, it's moving in this direction. And it's inside a magnetic field from left to right. And using the right-hand rule, number one, it's going to experience a force in that direction. Okay, so this magnetic force is given by this one. So V cross B is going to give you the force. That's it. All right, now this is for a single charge, but the current is number of charges moving in the same direction, right? So the current is Q over T. So this is the number of charges moving in that direction. So how do you turn this expression that has current in it? Look, guys, Q, V, charge moving in this at this speed is actually your current term. Motion of a charge, by definition, is what current is. Mathematically, this little combination that you're looking at, this is the description of a current, not only conceptually, but mathematically. So what is V? V is how fast the charges are moving through this length within this time period. All right. So V represents the speed, which means that this is the amount of displacement that the charges will go through the length of this wire within that time period. So the only thing you have to do is just take this term V, and express it in terms of its length within that time period. So you take this, plug it into here, and then it gives you a cute little expression. What is Q divided by T? This term becomes your current, and that's it. All right. So you end up getting the right-hand rule number one. Instead of using its charge expression, now you can express the same thing in terms of current. Okay, now you have to be a little bit careful in the way this formula is expressed. Current has magnitude, it doesn't have direction. But you can assign direction to the length, all right? By assigning direction to the length in this case, so you're expressing it in terms of displacement, so the displacement is going to have direction in this case. So the current is getting displaced along the direction of the length of the wire inside a magnetic field. All right, and then as a result, these charges going across the magnetic field will experience a deflection. It right angles to the direction of the current. That's what it means. All right, so that's the formula that we will get to use for this one. All right. Lecture review material. All right, so this becomes the formula. All right, so this is the formula for the magnetic force acting on a current carrying wire. All right, once again, it's the extension of the right-hand rule number one. The charges are getting displaced along the length of the wire. So there's current along the length of the wire inside a magnetic field, external magnetic field, in this case from left to right. So which means that the wire is going to get deflected in the direction indicated within this formula. All right, so what does this angle represent inside the formula? It represents the direction. It represents the angle between the direction of the current along the length of the wire and the external magnetic field.